Thank you very much, and good morning, everyone. I'm Kazumasa from University of Tokyo. First of all, let me thank the organizers, especially Thierry, François, and others, for this wonderful opportunity to give lectures in front of you here. And in addition, it's always a great pleasure for me to come back to France, especially this area where I spent quite a bit of time in the past. Okay, so my lectures will be about growing or random interfaces, in particular about the KPZ or the Kardar-Parisi-Zhang Universality class. And I believe it is one of the most important and successful milestones in statistical physics for systems driven out of equilibrium. This is because, firstly, this universality class describes a variety of phenomena, mostly out of equilibrium, not only random interfaces. Is it working? Yes. Not only random interfaces, but also some kind of polymers in disordered medium. Is it working? Sorry. Okay, fine, like this. Okay, so it's not only about random interfaces, but it also describes some polymers in random medium or particle transport problems, some fluctuating hydrodynamics, and way more. And the scope is still expanding. So that's the one reason why KPZ is important. And the second reason is that it turned out to be tractable by exact solutions, despite being nonlinear, non-equilibrium, and many-body problems. And such exact studies unveiled many non-trivial statistical properties which are universal in this kind of random problems. And also, it also led to developments in mathematics. So the beauty of the KPZ class is mostly in its mathematical and theoretical aspect. And that's why the lectures on random interfaces are also given by a mathematician, Ivan Cohen, in this school. But I would like to emphasize that, that KPZ is actually more accessible than than it's typically regarded. Actually, many of the outcomes can be understood also by intuitions of physics. And that's what I want to tell in this lecture. Okay? So in my lectures, please ask questions anytime if you wonder anything. Okay? And also, I put all slides as well as some hyperlinked references at this link. So it's better if you download when you have time, and then you can focus on what I say and what I explain. Okay? Okay, so let's go. First, I'd like to explain why we should care about this KPZ universality class. To explain that, I would like to put it in the context of physics of critical phenomena and scaling laws. So let me briefly mention the history of critical phenomena and scaling laws. It was built not only by theoretical breakthroughs, such as Onsager's exact solution to the Ising model, but also experiments played some major roles by finding the critical point of liquid-vapor transition, and also experiments in the early years showed the universality of exponents in this kind of problem. And then, as a result of such developments, in the end, as you know, it led to fundamental developments such as renormalization group theory and conformal field theory, and so on. And this kind of development is still continuing today. And as you know, these developments are about equilibrium systems, equilibrium critical phenomena. And here, I think everyone agrees that the Ising model and its corresponding universality class have played major roles. Now, if you turn your attention to systems driven out of equilibrium, then I believe that it is probably the KPZ universality class playing similar roles. I believe so because we are making some sort of similar developments in the sense that there are exact solutions about the KPZ class. There is a nice continuum equation, and that is the KPZ equation. And also, there are experiments that can be compared with predictions from exact studies. So theoretical physics and mathematics and experiments, all these are working in close relationship, and we are developing something new. So that's the motivation, one big motivation to study and learn about the KPZ universality class. Okay, so what is KPZ class about? So the main target of the KPZ universality class is random interfaces. So let me show some examples in nature about random interfaces. This is a video taken from Facebook. And this video shows park in Spain in early summer, probably like now. And it shows spreading of fire on fluff of poplar. So this park is covered with full of fluff of poplar, and fluff are extremely flammable. So just a small little amount of fire is enough to make this kind of spreading fire. And then you see clearly a border between unburned region and burned regions. And this shape of the front is interesting. Probably this fire started from a single point, just from a cigarette fire or something like that. So we would expect that if something is growing from a single point, it would produce a circle, right? But it's not just a circle. It has many fluctuations on it, and these fluctuations seem to develop in the course of time. And we find similar phenomena not only in this kind of fire spreading, but okay, so this is a model experiment corresponding to this fire spreading. But not only that, this is from my own experiment. By the way, I'm an experimentalist, so we do experiments like this. This is a turbulent convection in liquid crystal. And then we see a nucleation of some black turbulence followed by spreading. And again, you see similar fluctuations on the border. This is an experiment from another group. It shows deposition of colloidal particles on the edge of a droplet. And as a result of accumulation of particles, you do see this fluctuation of the surface of the accumulated particles, right? This is an example from more biological systems. It shows colony of cancer cells. So as you know, cancer cells grow and divide indefinitely. So it makes a colony, and the colony expands. And you see, again, some fluctuating edges of the colonies. And an important remark is that all these are about completely different processes in microscopic scales, right? Materials are different. Underlying mechanisms are different. Nevertheless, they share one obvious fact that all these are about growing regions with some fluctuations. And probably as a result, we do see similar interface fluctuations with many scales, right? There are small fluctuations. There are bigger fluctuations. And actually, these are scale invariant. So that's what the KPZ class is trying to deal with. OK, and let me explain a little bit what kind of quantities the KPZ class is dealing with. Let me take my experimental observation. This is the border of the growing turbulence of liquid crystal. And this example also started from a single point, right? So again, let me play this video. It started from a single point. So it makes roughly circular interface, but you see fluctuations. If it were a perfect circle, then the radius is the same everywhere at all angles. But because it's fluctuating, if you measure the radius at each angular position, it has some fluctuations. These fluctuations are denoted by delta H here. And if you measure the standard deviation of this delta H, so the fluctuation amplitude of this delta H as a function of time, then you find a clear power law. So this is a log-log chart. And you see a straight line. It shows a power law behavior. And the slope is very close to 1/3. And this 1/3 is the characteristic exponent of the one-dimensional version of the Kardar-Parisi-Zhang universality class. But actually, exact studies told us way more about the properties of the fluctuations. One example is that it tells that what kind of distribution these fluctuations show. And I will explain later in the second lecture, I think. But actually, thanks to Sylvia, I can already tell what kind of distribution it is. Actually, there is a relationship with random matrix theory, which Sylvia also told this morning. So here are the symbols indicate the experimental histogram from this experiment. And the solid line you see here, there is a blue solid line. And this is actually the distribution of the largest eigenvalue of GUE random matrices. That is called the Tracy-Widom distribution. I will explain the definition later in the second lecture. But here, I just want to remark that such experimentally observable fluctuations have connection to random matrix theory. OK. So this is something you will learn in the lectures. And also, as I said, the KPZ class is not only about random interfaces. So let me show some examples. So growing interfaces are, of course, one of the main phenomena described by the KPZ class. But it also describes some sort of stochastic particle transport. Suppose you have a lattice, and there are particles in some of the lattice sites. And particles hop to the neighboring site with some probability or rate, which is asymmetric between the forward and backward hop. And as a result, these particles will move stochastically in one direction. You can ask how the current fluctuates in this kind of system. And these are also described by the same universality class in some simple models. It's also related to a problem of random polymer, a kind of polymer that is directed along certain direction. And when this kind of polymer is placed in random potential, then again, in some simple cases, it is connected to the KPZ universality class. Like this, there are many other examples: starred fluid, interacting Bose gas, fluctuating hydrodynamics, some insulator with disordered potential, some quantum polariton condensate, and recently some quantum spin chains. So the scope is expanding very widely. And that's something in my opinion, very interesting when we learn physics on the KPZ class. And theoretically or mathematically, it's connected to many different objects, such as or many different theoretical concepts, such as integrable systems, random matrix theory, and combinatorics in mathematics, and of course probability theory, and so on. And actually, what I describe with blue characters are something that I want to mention in my series of lectures. Okay, so let me explain the lecture plan. The goal of this lecture is to understand what is KPZ and why or how it's connected to different problems that I explained in the previous slide, and what are the main outcomes of the modern developments based on exact solutions. To understand these are the goal of this lecture. And in my lecture, I would like to foster intuitive understanding of the outcomes rather than mathematical or technical details. Okay? And this is the table of contents. I don't explain each, but probably today I will explain basic properties of the KPZ class without assuming any prior knowledge on the KPZ class. So I will derive basic properties such as the scaling exponents and other essential properties. And in the second lecture, I will explain some main outcomes of exact solutions on the 1D KPZ class. And probably in the third lecture, I will explain experimental tests of predictions that were predictions from exact solutions based on some integrable models. And this is a table of contents that I put on the website. But let me change a little bit. I would like to shorten the chapter 6 and include it in the chapter 5. And as a replacement, I would like to explain a little bit about recent development or discussions on some mysterious link between KPZ and some quantum spin chain problems. Because this is something I consider important and mysterious, so there must be something new in the future. And that's why I wanted to explain it in this lecture. Okay? Okay, and before starting the main part, let me show some list of recommended reviews on KPZ. It was the year 2000 that exact solutions were found for the first time in the context of the KPZ class. So there are already a lot of reviews about modern developments on the KPZ class. And even before the year 2000, there are a lot of physics literatures, especially the important properties on the scaling exponents were already well documented before the year 2000. So I put some references from that, from this early epoch. And myself, I published some lecture notes in this journal. And my lecture here will be mainly based on these lecture notes published in this journal. And actually, I will also publish a textbook on the physics of the KPZ Universality class. I'm afraid it will be in Japanese, and it will be published near the end of this year. It looks like this. But I hope in the end, some English, I hope I also publish some English version of that. Okay. And about the review papers I put here, there are some review papers focused on some particular subjects in the big context of the KPZ class. So depending on your purpose, you may choose appropriate reviews. Okay, so that was the introduction. Any questions so far? Good. Okay, then let me proceed to the chapter 2. Here I will explain scaling exponents and in what conditions the KPZ class can be expected, and what kind of universality classes exist in the context of random interfaces. So again, let me show some examples from nature and experiments. This is the kind of interfaces that we want to describe. Okay? So all these are related to some random microscopic processes. That's why we need some stochastic process to describe this kind of system. Then let me begin with some warm-up toy example. Let's consider some model of random deposition of blocks. It is a lattice model, as you can see. So the spatial coordinates x are just integers. And you drop a block one after another at some constant rate. So let's say we drop a block one block per unit time, and we choose the position randomly. Okay. And dropped block just falls to the bottom of that site, and there is no interaction with neighbors. It is the simplest kind of model that you can think of, right? And then we can, what we are interested is the shape of the surface of the deposited particles. That is denoted by h, and h at position x is just the number of blocks accumulated at a given time. Okay, and we are interested in the fluctuation properties of this h. First, the mean value is quite simple. We just drop up one block per unit time, and the mean h is proportional to the total number of blocks. So it grows proportionally with time, right? Then what about the fluctuations? Fluctuations of h, delta h, are defined by h minus mean h. And then it's easy to show that it grows like t to the 1/2 because of the law of large numbers. That is because whether we have a particle or not is just a stochastic process. It's just a consequence of random number, right? Each site has the chance of having a new block at the probability 1/n. N is the number of sites, right? And the number of particles at each site is just the sum of such random numbers. And there is no interaction, no correlation in these random numbers. So just because of the law of large numbers, the standard deviation of h grows like t to the 1/2. Okay? And because of the central limit theorem, the fluctuations of h should be Gaussian at large time.
So
yes.
Do you look at the sort of absolute value of you want the sort of magnitude deviation? When it grows like t to the 1/2. Like you take an absolute value.
You can take the standard deviation. Not absolute value, but standard deviation. Well, you can, yeah, if you want, you can take the absolute value and take the mean, but the natural thing to do is to look at the standard deviation. Okay? Okay, now what we want to do is we want to have a coarse grain equation to describe this kind of process. We coarse grain, and we want to get some continuum equation of h as a function of continuous space position x and time t. And this is straightforward, and by using this fact, and it should look like this. dh dt should grow like some constant in order for the mean to grow proportionally to time. And of course, we have random fluctuations. And these fluctuations are just Gaussian and uncorrelated. So we can just add some white Gaussian noise, ether. The mean of ether is 0. And the covariance of ether should look like this, because it has no correlation in space and no correlation in time. And here you have some parameters, d here and v naught here. Okay? Okay, now we want to include some interaction.
Why do you say this is forced minimum?
Because we don't have lattice anymore. So we sort of take average over some length scale that is much greater than the lattice constant. And then everything can be described as a function h, as a function of spatial position x, which is some real number, and time t. Okay. And now let's introduce some interaction between blocks. Now suppose, so basically the rule is very similar, but the only difference is that after each drop of the block, when the block arrives at the bottom, then it looks at neighbors. And if this block finds a lower surface than where it is situated, then it goes to the lower neighbors. So this block has two lower neighbors. So it chooses one of them at random. This block falls here, and it doesn't have lower neighbors, so it stays here. This is a new rule. Yes?
Does this dropping happen more than once? So if it drops one, and if it can go lower, it drops again?
No. It just goes to a neighbor, and that's the end. One neighbor.
Yes.
Yeah. Yes?
So in this case, how do you make this configuration? Like, how can you build up a tower if they always fall to the lowest neighbor?
Oh, okay. Yeah, sorry. Thank you for that question. So it can choose lower neighbors stochastically. So it has a chance to go to lower neighbor, but it also has a chance to stay where it is. But it's a matter of choice. You can change the rule and it doesn't affect much. Okay, so now we have this rule. And it's straightforward to do some numerical simulations of the model. And this shows the effect of this new rule, the surface relaxation rule. If we don't have such surface relaxation rule, this is the interface you get. And as you can easily imagine, the interface is quite rough, and it's not differentiable, obviously. But if you have relaxation rule, then the fluctuations are much more suppressed. But you still have some fluctuations. And to describe this process by a continuum equation, you can just include the effect of this surface relaxation, and this can be written down as a Laplacian of H. Because if you have a bump like this, then you have a smaller chance to get a new particle. If you have positive curvature, then you have a higher chance to get new particles. That gives the Laplacian term to the continuum equation. And this equation is called the Edward-Wilkinson equation. And this defines a universality class on this kind of random growth problem. Yes?
Can you actually derive the surface tension and the statistics of the noise from the microscopic parameters of the model?
derive mathematically?
Yeah, like if you have a microscopic model, can you do the first one?
I believe so. I don't know any particular real literature on that, but it may exist. I just don't know, and I believe it's possible.
Yes. Is V a constant?
This one, mu, is constant. Yes.
So that new term seems to allow also the blocks to jump up, or it's only jumps, the blocks can only jump down. It looks like just a diffusion that we take the block move up and go down independently.
So there are a few points. So one is that indeed it looks like diffusion, but diffusion term. The most well known is the diffusion equation, right? But in diffusion equation you have the probability. Here we have H. But indeed this diffusion-like term has the effect of suppressing the fluctuations. So that's why it tends to show this kind of smooth, less rough interface. And another remark is that this is a stochastic process. So at least in this coarse-grained equation, there is a possibility that a positive fluctuation can be even more positive, and lower surface can be even more lower. But on average, positive or negative fluctuations tend to be suppressed because of the diffusion. Okay. Okay, and then let me explain a few properties of this Edward-Wilkinson equation. First, one obvious remark is that we can just erase this constant term V0 by this variable transformation. If you define H prime by this equation and you plug it into this Edward-Wilkinson equation, you can of course delete this V0. So in the literature, you find equation without this constant term often. And then what we want to know is what kind of scaling laws describe the interface in this Edward-Wilkinson equation. To get scaling laws, we can assume that solutions in this equation have scale invariance. So suppose solutions are statistically invariant under the following scale transformations. So suppose we change we change the scale of x by factor b. Then we change the scale of t by factor b to some exponent z, and change the scale of delta h by factor b to another exponent alpha. And suppose that the equation does not change its form by this scale transformation. So you can plug these equations to the Edward-Wilkinson equation, and you choose the value of z and alpha in such a way that the equation for x prime, t prime, and h prime look exactly the same. Then you get this relationship about the exponent. So this b to the alpha minus z comes from the left-hand side. Okay, if you plug this and this, this and this to the left-hand side, you get b to the alpha from h, and you get b to the minus z from this t. So you get b to the alpha minus z. If you just do the same for this diffusion term, then you get b to the alpha from h and minus 2 from Laplacian. And this should be balanced with the left-hand side. For this ether, you remember ether is characterized by this covariance. And when you change the scale of x and time t, these delta functions are also transformed, and you get b to the minus 1 from space and minus z from time. And this is about eta squared. So for eta, for this eta, you have the factor b to the minus d. D is the dimensionality, space dimensionality, d plus z divided by 2. And you assume that all these are balanced in order for the equation to look exactly the same. And then you get this relationship about the exponent z alpha with space dimension d. And this better describes how the fluctuation amplitude grows with time. So from this scale transformation, you can already know that delta H should grow like b to the alpha, and b is proportional to t to the 1 over z. So if you plug it into here, you get delta H proportional to t to the beta, and beta is defined by alpha over z. And this beta is of course given by this equation by using these two relationships. So you obtain the values of the characteristic exponents alpha and beta and z for this Edward-Wilkinson equation by this kind of simple scale transformation. And these are the characteristic exponents of the Edward-Wilkinson Universality class. Yes?
So why do we choose the scale transformation that's useful?
Excuse me?
Sorry, why do we choose the scale transformations like this for?
So we assume the scale invariance. The meaning of the scale invariance is that even if we change the scale of variables, so the variables we have are the space dimension, space x, and the height h, and time t. These three are sort of different dimensions of the problem. And if we change the scale, so if we zoom your So this is the interface, and what the scale invariance say is that if you take a piece of the interface and you zoom your image by some factor along the x direction, you also zoom your image along the h direction by another factor. And you also change the time. So as a course of time, you have another interface. So you take a piece of interface from another time, you zoom it accordingly in the x direction and h direction. And what the scale invariance says is that if you choose the factors of the, zoom factors in the x, h, and t directions appropriately, then your zoomed image looks exactly the same in the statistical sense as the original picture. This is the meaning of the scale invariance. And if you describe, and this is just the, this equation just tells how you zoom each variable. And of course, the zoom factors can be different. So I just put some unknown exponent for each. Thank you. Okay. So that's the Edward-Wilkinson Universality class.
Yes. So D equals 2, alpha and beta vanish, and then above D equals 2.
Yes, that's a great point. So for 1D interfaces, you get alpha 1/2, beta 1/4. So the fluctuation amplitude grows like t to the 1/4. But for two-dimensional interfaces, as you remarked, beta vanishes. So actually, this is the what is called the upper critical dimension. So for the Edward Wilkinson Universality class, if your interface dimensions are above 2, then you don't have rough interfaces. And 2 is a critical dimensionality. So you may get some non-trivial correction. Okay. So this is the Edward Wilkinson equation. And as I already said, it is quite straightforward to know the exponents characterizing this Edward Wilkinson equation. And it is linear equation, linear in H. So it's easy to handle. And you can readily get general formulas from general initial conditions. But one problem is that it is a bit unnatural. The reason is that this Edward Wilkinson equation is written down for the variable h. And the variable h is the height of the interface. So it is defined in the upward direction always. It means that even from such a bump of interface, this interface tries to grow upward always because you have this growth speed v0 here. But in many examples of interfaces in nature, if you have such a bump, then it's more natural for this interface to grow in the direction normal to the interface. Right? So this kind of growth assumed in the Edward Wilkinson equation is something a bit unnatural from the experimental viewpoint. We want an interface that grows like this. And to include this effect, what we can do is that we can change the direction of the axis locally at each point of space. For example, here, we assume that this interface grows in the normal direction according to the Edward Wilkinson equation. And then we can get an interface at a time step later. And then we can transform the location of this interface to the original axis h and x. So something like this. To write down the local growth of the interface, we can use the local axis h local, which is the normal direction, and x local, which is the tangential direction. And dh, the evolution of the interface, is given by the Edward Wilkinson equation. And then we can change these dh local and dx local to dh and dx, as written here. And this can be transformed straightforwardly by using the angle theta, which is defined by this. And dh is related to dh local by this equation. And if you just keep the lowest order nonlinearity here, you get gradient h squared 1/2, and you get this KPZ, this equation. And this is what is called the Kardar-Parisi-Zhang equation, KPZ equation. And it was written down by Meheran Kardar, Giorgio Parisi, and Yi-Chen Zhang in 1986.
Yes. So for me, it's it's actually a bit natural to think of the Edwards-Wilkinson equation in the limit where the ball is really large. So the curvature is small, and you have almost a plane. So in the case when the ball is really, really large, it's like a smooth plane. And also it's flat, and then this equation takes over.
So the answer is actually not. Even if the average profile looks smoother and smoother, you always have fluctuations, and you always have the effect of nonlinearity because of these fluctuations. So you have locally tilted interfaces. You always have the effect of this nonlinearity from such local fluctuations. And what we get is that the fluctuation properties are different from what the Edwards-Wilkinson equation predicts. So this nonlinear term is crucial, and it cannot be omitted. Other questions? Yes.
Would it change anything if you try also to treat the noise like this? Say you consider noise that is always at something in normal direction and you rotate it? Would it change?
So we assume uncorrelated noise, Gaussian noise, uncorrelated in space and time. So at least under this assumption, we can change the how to say, even if we change the axis as illustrated here, we can always use the same eta of x and t because of the absence of correlations. And even if there is a correlation in short range, even if we have short range correlation, if the scale of description becomes much large, then there is no effect from the short range correlation, and we end up with the same equation. Okay, and this KPZ equation is characterized by another set of exponents. I will show this later, but just to give you the result here, for one dimension, alpha is 1/2, and it is the same as the Edwards-Wilkinson equation, but beta is changed, and it's now 1/3. And since z is defined by alpha over beta, z takes a value 3/2. And this set of the exponents characterizes the KPZ universality class. So basically, if you observe some interfaces from simulation models or from real experiments, and you measure the exponents, and if you find this set of exponents, you can say, practically speaking, you can say this is in the KPZ class. Yes? Excuse me? Oh yeah, if lambda goes to 0, it goes to Edwards-Wilkinson equation. So actually, for small lambda, we have crossover phenomenon from Edwards-Wilkinson to KPZ. So at short times, you see the exponent of the Edwards-Wilkinson equation, but at a larger time, it crossovers. So beta changes from 1/4 to 1/3. Yes.
Can you record how do you define theta?
Theta here. Yes. So theta is just the tilt angle of the interface. So you can just define by this. I mean, tangent theta. Theta is just the arctangent of tangent x.
Yeah, but since the interface is rough.
Oh yeah. Yeah, that's a good point. So it's not trivial if we can really do this kind of thing with rough interfaces. So here, so I will come back to that point later, near the end of today's lecture. So here, I just resort to rely on the mean profile of the interface, which can be smooth. And we just assume that theta is defined by this equation, And if we assume that, we get this equation. But actually, this equation turns out to be not well defined. So we have to be careful what it means about discussing what it means. And I will explain this later in this lecture. Yes. 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 Yes.
You added a new
Yes. Yes. Yeah. Actually, we cannot do the same thing for the KPZ equation. Generally speaking, the values of the coefficients may also be renormalized. So we have to be careful to do this kind of scale transformation calculation. And it turns out that in the case of the KPZ equation, this naive scale transformation gives a wrong result. And if you do more refined calculation by using one loop approximation, for example, I mean, there is a technique to evaluate how these coefficients change with scale transformation. And then it turns out that nu and d, the variance of this noise term, will be rescaled with scale transformation. And as a result, yeah, we cannot use the same trick, but we can derive this set of the exponents by different method. And we can also do the same on the basis of that renormalization calculation as well. Yes. Other questions? Yes. Yeah. You asked how we define. You are asking about the values? Okay, about the values, I will explain later. I don't explain yet. I just tell the fact. I will derive later.
Yeah, but actually, since I didn't explain, if you scale it as before, you will not be scaling invariant.
Okay, so the scale, the meaning of the scaling invariance is not that. Okay. Yeah. So actually, in the case of the KPZ equation, when you change the scale of the description, it's not only the variables h and x and t, but also some of the coefficients, specifically nu and d here, will also change. So it's hard to see that the KPZ equation remains invariant under the scale transformation at this point. If you need to do some detailed calculations on the related to the scale transformation. Yeah, but the fact is that this KPZ equation remains invariant under this choice of the exponent. I mean the scale transformations with this choice of the exponent. And I can derive these in a different approach later.
I don't think it's correct what you're saying. It's not, the equation doesn't remain invariant. It's the infrared physics which remains invariant. The equation is microscopic, it doesn't remain invariant. I think what you're saying doesn't make sense from a realization group point of view.
I mean, the coefficients will also be renormalized.
But your confusion, the UV description and infrared physics, which is a big mistake.
Yeah, okay. Yeah, I mean, okay. So maybe more precisely, if we look at the interfaces, then interfaces are scale invariant, and by change of the variables, they look statistically invariant. Okay. So let me give some remarks on the KPZ equation. KPZ equation is this. And again, similarly to the Edward-Wilkinson equation, this constant term V0 can be omitted by the same scale transformation. And KPZ equation has some important symmetry. So KPZ equation is invariant under the following transformations. The first one is time translation. The second one is space translation. You can easily check it. The third one is space inversion and space rotation in the case of higher dimensions. I mean 2-dimension and higher. And it also has height translation. And actually, the invariance under the height translation is important because actually this is why we get scale invariance from this kind of equation. In the theoretical physics, it is known that if we had a term like minus AH, so if we have a term proportional to H, then we don't have a scale invariance. If you know critical phenomena, we can write down the equation for the order parameter. For example, if you know the Ising model, you can write down an equation, coarse-grained equation for the magnetization. And then, according to the Ginzburg-Landau theory, if you write down the term for magnetization, time derivative of the magnetization, you have a term like minus T minus Tc times phi. So in the case of the Ising model, you coarse grain, you write down the equation for the magnetization phi, and then you have a term like this, and then you have a higher order term, diffusion term, and noise term. And what is known is that if you have this term, then you don't have scale invariance. But in the case of the critical phenomenon, at the critical temperature, this term vanishes, and then you can get scale invariance at the critical point. In contrast, in the context of the growing interfaces, we typically have invariance under the height translation. So the location of the substrate, the reference substrate, has no effect on the interface, and then you have this symmetry. And in order to satisfy this symmetry, this kind of term is forbidden, right? And this amounts to being at the critical point in the case of the critical phenomena. So thanks to this symmetry, we always have scale invariance analogous to the critical phenomena in this kind of growing interface problems. So we don't need to fine-tune your parameter, but we always get some scale invariant fluctuations in this kind of problem. Okay, and then it is known that KPZ class generically arises if you have this set of symmetries. An important remark is that we don't need isotropic growth condition that I assumed when I derived this KPZ equation. It is one way to derive the KPZ equation, but it is not the only way to get this nonlinear term. The source of nonlinearity can be anything, and if this set of symmetry is satisfied, then we typically get this nonlinearity as the lowest order contribution. You also have higher order contributions, but these can be shown to be irrelevant in the scaling properties, and you get the KPZ equation, or KPZ universality class. One example in the context of deposition problem is what is called the ballistic deposition model. So in this model, again you drop blocks one after another. But when the block falls and when it finds a neighbor like this, then this block sticks at the highest point of the neighbors, like this. This is the rule of the ballistic deposition. And this is nonlinear interaction, nonlinear in H. And as a result, you get, in the coarse grain scale, you get the same nonlinear effect. And this model is known to show the exponents of the KPZ universality class. Okay, so that's why, physically speaking, KPZ examples of the KPZ class can be found in many kinds of models of growing interface.
Yes. In the case of this ballistic deposition, yes, the microscopic model would have a multi-valued H. So in the KPZ equation, should I imagine there's some average for each X? Or?
Right. So when we define the height in this kind of model, we typically look only at the highest point at each lattice site. In this way, we define a single-valued function h, and then we get the KPZ exponents. Yes?
When you say you get the KPZ exponents, so is this like exactly solvable somehow, or is it kind of like through simulation you see the power laws arise?
In the case of the one-dimensional space, we can derive the exponents rigorously. But for higher dimensions, for dimension 2 and higher, there is no exact values known for the KPZ class. So we need to resort to simulations, and we get we have rather precise estimates for.
And just believe they still fall into this class at higher dimensions. And based on these estimates, they look like they should fall into the same class at higher dimensions.
So the exponent values depend on the dimensionality. Yes.
Thank
you. Okay.
Okay.
Good. Then let's go to the chapter 3. And here I'd like to explain some basic properties of the KPZ equation. First, let me explain that the KPZ equation is related to some fluid problem. So let me begin with the KPZ equation, and I would like to omit the constant term V0 here. And let's define a new variable V by this. So minus lambda times gradient H. So you just plug it into this equation, or you consider the time derivative of V and use the KPZ equation to transform everything, and then you get this equation. This equation looks pretty much like a fluid equation, like the Navier-Stokes equation, if you know this. But in the case of the Navier-Stokes equation, you have pressure gradient in the right-hand side. Here you don't have the pressure gradient, and this equation is called the Vargas equation with some random forcing term. So with this random term, this equation is called the noisy Vargas equation. And Vargas equation is known as a kind of toy model for fluid. And it is a nice model to describe a nonlinear phenomenon, fluid phenomenon, like shock waves. So there is a lot of literature about that. And the KPZ equation is equivalent to this noisy Vargas equation. Then, as a fluid equation, it has some symmetry. One important consequence is that this noisy Vargas equation must be invariant under Galilean transformation defined by this. You can easily check that this noisy Vargas equation has this symmetry. And this Galilean symmetry must be kept the same under scale transformation. I mean, fluid must look fluid even if you change the scale of the descriptions. So in order for the same Galilean transformation or Galilean symmetry to hold, we can show that this advection term, I mean this term, should have coefficient 1, even if we do scale transformations. It means that the coefficient here of the advection term is not renormalized by scale transformations. Now let's remember this, and let's adopt another definition of the field V. If we define V instead of minus lambda gradient H, but just minus gradient H, then from the KPZ equation, we get this equation, and now we have parameter lambda in this advection term. But we have just learned that the coefficient of this advection term is not normalized, is not renormalized by scale transformation. So lambda is invariant under scale transformation. Then we assume again the scale transformation I described in the other slide. So x is changed to b times x prime, and h is changed to b to the alpha times h prime. And we know this lambda is not renormalized, so we can balance the first term and the second term in the left-hand side. And then we get this equation. And from this, we get alpha plus z equal to 2. This is a consequence of this Galilean symmetry, and it's known to be valid for any dimensionality D. Yes?
In what sense you use the word renormalized?
So we consider scale transformation, and then if we change the scale of the description, so we ask how the time evolution equation of the new variable h prime should look like, starting from the KPZ equation, for example, for the variable h. And then we assume this scale transformation, and we want to get the time evolution equation for h prime. And then we can write down the what kind of terms we may have in the if we go to the momentum scale, momentum space, and we can write down the effective equations. And then then we want to get how the coefficients of the new equation, what is a good way to relate the coefficients of the new equation and also the variables as a function of the this transformation factor B. So yeah, so this is a procedure called the renormalization group transformation in physics literature, and roughly speaking, this is the meaning of the renormalization I mentioned. Yes?
Does the critical exponents depend on lambda?
No. So as long as lambda is not 0, you have the same critical exponents.
Okay. Yes. Is it necessary to use the relationship that we're
to get this?
Yeah.
Well, if you ask necessary, it is not. You can write down the renormalization group calculation directly to the KPZ equation, and then you can find that lambda is indeed not renormalized. So we can take that approach to show the same thing. But if we use this relationship to the Vargas equation, then we can rely on the property, I mean symmetry property as a fluid, And then we can get the same equation by this kind of elementary calculations. OK. Then let's go to the next one. Here, I'd like to explain the stationary state of the 1D KPZ equation. And to explain that, let me explain a little bit on something general about stochastic processes. So suppose a variable xi, like the position of a particle, evolves according to this time evolution equation. This is called the Langevin equation. Eta I is some white Gaussian noise. And we can describe the same kind of stochastic process, not in terms of the particle position, but in terms of the probability. So if we write down the time evolution equation for the probability, then it's known that this Langevin equation is equivalent to this equation for the probability, and it is called the Fokker-Planck equation. Then, so this is a, here I consider multi-particle cases. So we consider not only a single particle, but we can have many particles, and I is the index of the particles. Then in the case of the field problem, we have stochastic variable h as a function of x. You can discretize space x, and the continuum space corresponds to the limit of infinite number of lattice sites. So from this, you can get the corresponding equation for the Langevin partial differential equation, like this. And the corresponding Fokker-Planck equation looks like this. And here the right-hand side is described by using the functional derivative here. And functional derivative can be understood by this kind of replacement, if you want. So what I wanted to tell is that if you have this kind of Langevin PDE, you can get the equivalent description in terms of the probability functional for the field H. Now, in the case of the Edward-Wilkinson equation, this equation looks like this. So if you plug it into the equation I showed in the previous slide, then you get this Fokker-Planck equation. If you are interested in the stationary solution, so if time derivative of this p is 0, and if you solve the equation for this case, you can get the stationary solution to the Edward-Wilkinson equation in terms of the probability functional. And in the case of the Edward-Wilkinson equation, it's easy to show that this is the solution to the Fokker-Planck equation if you don't have the left-hand side.
Yes. In fact, I mean, if you look at the height variables themselves, they will never go to the stationary state because there is a zero mode of this. You have to subtract off the zero mode. Otherwise, P of h, t will never be time independent.
Sorry.
H function is the sum over all x, right? If you sum over all x, you see that it's just del square is equals to 0, so you have to sum over noise.
Yes.
So the zero mode, k equal to 0, always diffuses. So if you say that the joint distribution of the heights at different points goes into the stationary state, that's correct. And you have to subtract off the center of mass. Only then it goes to a stationary state. So this statement is P, Edward-Wilkinson's is h of x stationary. It's actually then it is the relative height.
Yes. Yeah, so we omitted the constant term, and yeah, right. Thanks for that point. So generally, so as I said, we can omit this constant term v not here, which existed, but okay, yeah, zero mode, yes.
So without the zero mode, I mean, it never go into a stationary state.
Okay, yeah.
It's an infinite system.
Yeah.
Give me the finance system. Give me the finance system.
Yeah, thanks. Okay, yeah, so that was the underlying assumption I made here. We assume there is no zero mode. So the space integral of H is 0. And then, we can get a stationary solution. So it's easy to check that this equation satisfies the Fokker-Planck equation, because you can basically group the two terms in the right-hand side with the same functional derivative. And if you calculate a single functional derivative to this, then you get something that that cancels the first term, and you can check that the two times cancel each other and vanish. So this is a stationary solution. And the meaning of this probability functional is that it tells that actually the stationary solution of the Edward-Wilkinson equation for 1D is equivalent to a Brownian trajectory. So suppose we have a Brownian particle, and the vertical axis is the position of the Brownian particle, and the horizontal axis is the time of the Brownian motion, and then the trajectory of the one-dimensional Brownian motion may look like this. What this result tells is that if you interpret B as the interface height, and if you interpret T as the interface position, then this trajectory actually gives realization of the stationary solution to the Edward-Wilkinson equation in the 1D case. But for that, we have to choose the diffusion coefficient of the Brownian motion appropriately according to what we have here. And this is given by this relationship. So suppose B is the standard Brownian motion, or the Wiener process, defined by this mean square displacement. And then if you multiply this B by square root of A is defined by D over 2 nu. And then you get one realization of the stationary solution to the Edward-Wilkinson equation. And from this fact, because mean square displacement of the Brownian motion scales is proportional to the lag time, it means that the fluctuation amplitude in this direction, in the vertical axis, is proportional to the square root of the scale in the horizontal axis. And in the language of the interface, it means that the fluctuation amplitude of H is proportional to the scale in the x direction, square root of the scale of the x direction. And this 1/2 is nothing but what we had at the exponent alpha. So from this result of the stationary solution, we get alpha equal 1/2 for the Edward-Wilkinson equation. Now let's turn to the KPZ equation. For the KPZ equation, we have this term. So in the Fokker-Planck equation, we have this additional nonlinear term here. And for general dimensions, now we basically cannot solve this. But one exception is the case of the one spatial dimension. And for the 1D case, we can actually check that the stationary solution to the Edward-Wilkinson equation, that is this, is also the stationary solution to the KPZ equation's Fokker-Planck equation. So basically, you can check that with this probability functional, you can check that this new term vanishes for the 1D case by using the partial integral. And this means that the exponent alpha is also 1/2 for the 1D case, 1D KPZ class. And then we already know that thanks to the Galilean symmetry, we have alpha plus z equal to 2 for the KPZ class. So by using this and that, we get z equal to 3/2. And beta is just alpha over z, so beta is 1/3. In this way, we can derive the set of the characteristic exponents for the 1D KPZ class. Okay. Yes.
Do you have them balanced with the noise, the scaling?
Sorry?
Do you have them balanced the scaling with the noise scaling with eta? Is that compatible with the?
So the effect of eta is here in the second derivative term of the Fokker-Planck equation.
For the scaling down there?
Lambda.
The scaling at the bottom, is it compatible with the with the scaling of eta or not?
Yeah, I mean, all necessary variables are rescaled, and so that rescaling is, so this is, here I use this only to show that the stationary solution to the KPZ equation is given by the Brownian motion, this. And then to derive this relationship, we considered the scale transformation, and we found that lambda is not renormalized, and then we get this. And by combining this and that, we obtain this set of the exponents. Good? Okay. Okay. Then, probably in the remaining time, let me explain about the well-definedness of the KPZ equation. Here, I have a very bad news. That is, we discussed so far about the KPZ equation, and I will discuss about the KPZ equation in my entire lecture. But actually, the KPZ equation is not well-defined mathematically. And the reason is very simple. This is the KPZ equation. And this eta was white Gaussian noise. It's uncorrelated in space and time. So it means that this eta is discontinuous everywhere in space. So it's very pathologic object in the mathematical sense. But here, you are saying that, so because of this eta, your h also becomes quite irregular in space. But in the right-hand side, you say that we need to compute the spatial derivative of h. So this is problematic. But actually, it's not that bad for the Laplacian term, because roughly speaking, Laplacian can be either positive or negative. So the effect of this irregularity goes to both directions. So if we take statistical average, for example, if we consider the mean value, the two effects, two contributions cancel, and the statistical values may have some well-defined values. So the diffusion term is not problematic. But this nonlinear term is not as good, because it says that we compute gradient h, and then we take square. So this term is always positive. So we don't have cancellation of positive contributions and negative contributions. So we expect that if the interface is rougher and rougher in space dimension, this term is getting larger and larger. So probably we cannot define the continuum. The continuous limit is not well defined. So what is known is that this KPZ equation as is actually mathematically ill-defined. And of course, we can circumvent this problem by writing down this equation on a discretized space. For example, if you do simulations, we can evolve this kind of equation on a discrete lattice. But then we can actually check numerically that if you decrease the lattice constant, the interface grows faster. So again, the time space continuous limit is not well defined, even in the physical sense. So the interpretation of this KPZ equation is not very trivial. So we have to understand how we can actually define this equation. And without understanding that, it's not clear what we mean by the KPZ equation and what we mean by exact solutions to the KPZ equation. And the answer to this problem is established at least for the case of the one-dimensional space. And there are basically two ways to make sense of the KPZ equation. One is called the Kohlhoff approach, and this is something I'm going to describe probably in the beginning of the second lecture. And another is something called Hayer's rough path approach or regularity approach. But this one is quite abstract mathematics. So let me use Kohlhoff approach to explain how we can define the KPZ equation properly. Okay, and I think it's a nice time to stop. So if you have some questions, I can take, and otherwise, maybe I stop here. Good. Okay, thank you very much.